Hello and welcome back. This section, section 2.4, will be all about correlation and how to see correlation in scatterplots. So to begin with, we should start with some definitions. So the first thing we want to look at is what does it mean for two variables to be correlated? What is correlation? And this is just when the values of the variables are associated with one another. And this could be by accident, or it could be because one causes the other. So, for instance, if you were going to look at painting a room, the length of the room will be correlated with how much paint you'll need. A longer room will need more paint. So, because these variables are related to one another, we say that they are correlated. But this could just happen by accident as well. A particular type of correlation is called linear correlation. And essentially what this means is if you were to plot the data, you will see a straight line appear in the data. There can be other ways that things could be correlated. There could be exponential correlation, where one variable is related to a power of the other variable. But with linear correlation, it's just going to be a straight line. And when I say that we plot the data, what I mean is we're going to look at a scatter plot. This can also be called a scatter diagram. And the idea is that we pair the data. So we look at two pieces of data and we pair them. This has to be quantitative, so these has to be numbers. And when we plot the data, we use the horizontal axis for x, and then the vertical axis for y. So the first one is always x, and the second one is always y. And I'll take a look at a couple of these plots here. So this is just coming from the book. Here we have a couple of scatter plots. This first one, they're relating waist circumference to arm circumference. And you can kind of see that this looks like a line going up and to the right. Now it's not perfect. They don't fall exactly on a line, but it does seem like these are going to be correlated. The bigger waist you have, the bigger arms you would have is essentially the take-home message from this plot. Whereas this one, this is weight versus pulse rate, so how fast your heart is beating. This does not look like it's gathered in a line, not in any direction, either up, down, left, right, or anything in between. It looks like these points are scattered pretty well, and they don't form a line. So here we might see some linear correlation in the left and no linear correlation in the right. And there are a few other things that we can learn. So for instance, this scatter plot is looking at weights of pennies and the year that they came out. So we can see on the left-hand side is the year on the vertical axis. So pennies that came out before 1980 look like they're sort of clustered over here, whereas pennies that came after 1980 look like they all weigh about 2.5 grams. So here we can get some information where before and after 1980, maybe the pennies were made differently, would be a potential hypothesis here. So these clusters and the gaps in between them can help us learn a lot about how variables may be related to one another. Remember that correlation does not imply causation, so just because two variables are correlated doesn't mean that one causes the other or vice versa. They could both be caused by something else, or it could just be random happenstance. So one question could be, how can we tell if something is, how can we tell if two variables are linearly correlated? And there is a number that we can compute. This number is normally called R, and this is the linear correlation coefficient. There are other numbers that they can compute to see whether or not things are correlated, but this is a fairly standard one. We won't look at how to compute R by hand in this chapter, but we will look at how to compute it using a computer, and I'll do this in another video, essentially in a spreadsheet. So R can take values between -1 and 1. So it could be something like 1/2, it could be something like -1/3, but it will always be between 1 and -1. And the idea is that the closer R is to 0, the less linearly correlated these numbers are. But when R is going to be closer to 1 or to -1, the two extremes, we will say that the two variables are going to be linearly correlated. But I have when R is close to 0 or when R is close to the endpoints, 1 and -1. But in statistics, we want to be a little bit more rigorous. So the question is, how close is close enough? When can we say, oh, this is close enough to 0 to say they're probably not linearly correlated? Or how close to 1 does it have to be? So the idea is that with when we're using R, there are going to be critical values of R. And this will just come from a table that we'll look at. And the idea is that this will determine, the value of R will determine, the critical value of R will determine how close we need to be to 1 or to 0 or to -1 to say we are not linearly correlated. Also, the critical value of R depends on how many pairs of data you are looking at. When you are looking at fewer pairs of data, so if you only have 4 data points, we'll have to be really, really close to 1 to say that they're linearly correlated. When we have 12 data points, we don't have to be as close to 1 in order to make the same conclusions. So how do we use the critical value of R? Let's assume that we have 5 data points, so we'll use a critical value of 0.878. I'll just draw a little number line, and we've got -1, 0, and 1. And the critical value of R, we will also plot this. This will be out here, so this is about 0.878. And over here to the left will be about -0.878. The way that we determine whether or not we're close to 0 or we're close to 1 is which region we are in. So to be close to -1 or to be close to 1, we have to fall outside of this region. So this implies linear. When we're close to 1 or close to -1, when R, is close to 1 or close to -1, we assume that we're linear. If we are in between, we'll say we can't say that it's linear. Can't say there is linear correlation. And again, I don't want to say that it's not linearly correlated. I want to say I can't conclude that it is linearly correlated. So just to clarify, when we fall outside of the critical values, so closer to 1 or to -1, then we can say linear. And a more explicit way of saying this, we could say that there is sufficient evidence that the variables are linearly correlated. When we're in between those values, when we're in between the critical value and negative of the critical value, we can't say that it's linear. And again, one way to say this is there is insufficient evidence to support the claim that the variables are linearly correlated. When we're doing statistics, we have to be explicit here. When we're between those two values, we're not going to say not linear. We're going to say we don't know. There's not enough evidence to say that they are linearly correlated. And again, to really drive home this point, the question that we're trying to answer is, can we say that the variables are linearly correlated? If we're outside of the critical values, yes, we can say that. If they're in between the critical values, nope, we can't say that they're linearly correlated. In the next video, I'll look at how to actually compute R given some data in a spreadsheet.